Hello and welcome! If you have been keeping up on our videos, you saw the last one where I finally successfully called into the random subroutine from the basic ROM. So now I can get some random numbers. Today we're going to explore how to do that more efficiently. And in the process, we will use structs in assembly language. We will have the debugger coerce code into scenarios to make it easier to debug. And we're going to call the subroutine INTCNV from basic ROM in a way it was not intended to be called. Ooh. You are watching the hello world of random numbers. Now that we can make random numbers, what do we do with them? We put garbage on the screen. So each location of the screen buffer is filled with a random byte from 0 to 255. Glorious! But slow. In fact, let's just speed it up using turbo mode.
Let's hit the turbo. Very good thinking, Mike.
That's faster. But it still feels kind of slow, doesn't it? I mean, you can see it go. I kind of thought it would take, less than a second to fill the screen. I thought like the whole screen would sparkle like static noise. So let's take a look at the code. So it's all happening starting here with fill with garbage. We point X to the screen buffer. We get ourselves a random byte. And then we put that byte into the screen buffer and continue. And until we reach the end, we just keep looping. That's basically it. One random byte is code like you've seen before. We just fill up our floating point accumulator with the appropriate number. In this case, it's 256. And then after we convert the result into D, we subtract 1. So we have it in the range from 0 to 255. What can we do to speed this up? In fact, what is responsible for the slowdown? I tried commenting out code to see which made the most difference, what improved the speed the most. And I improved the speed the most when I just don't call R&D. I was hoping maybe there was something about INTCNV that I could do differently or whatever, but really, this dude right here is what's so slow. So then it occurred to me, when I convert to an integer, I end up with the answer in D, and that is a 16-bit register. I should be able to double the speed if I just make my random numbers not go from 0 to 255, but from 0 to 65,535. Then I can do 2 bytes at once. Let's give that a try. So here's the updated code. We're now going to pass 65536 to R&D, and that should give us a number between 1 and 65536. And then if we actually get 65536, we're just going to wrap it around to 0. So that'll be how we get our 0, and then 65535 will actually be the max we can get. These are the floating point accumulator values to do that with. And fill with garbage is just a little bit different. Now we get 2 random bytes instead of 1, and then we'll have them in our D register, which I can then store wherever X is, and the plus will advance X 2 bytes instead of 1. This should double our speed. 2 random bytes is the same as we saw before. Only difference is I have this code here to wrap around. It's a little bit sleazy, so it's probably worth mentioning what I'm doing. But I call the random subroutine, and then I check out what happened in the exponent. So if I get 65536, my exponent is going to be hex 91. That's how many times you're going to need to shift a single byte to get that high. And this is the only way I'm going to get hex 91. There's no other value that RAND can return that will give me that exponent, because 65536 is the max. 65535 is going to be 1 less in the exponent. and everything else will be less than 91. So this is kind of my sleazy way of saying, did I get 65536? Just checking the exponent. And if not, then I just skip and I go ahead and do the conversion. If so, I wrap around to 0. So I just change D to be 0, and that's it. So should work, right, folks? You don't see anything wrong here, right? As always, I write flawless code with no bugs, right? What happened here? It looks like we got 1, 2, 3, 4, 5. This makes 6 bytes, so we were able to run it 3 times. And then FC error? What could be responsible for the FC error? One way to narrow that down is to kind of start commenting out which subroutines that we're calling, and it's really just 2. It's R&D, and then it's the int conversion. So I could comment out this, and then, just convert whatever's in D, but that's probably not going to be the right thing, because it's probably whatever this return that would have caused this. But I could just comment this out and see, and Rand kept on going fine. So there was some value that R&D returned that int convert did not like. And when I narrowed it down, I checked the Unravelled book. Int convert starts over here, and the very first thing it does is it checks for something and it'll give me a type mismatch error if we're looking at a string variable. That's not the problem. That's not the problem. We're not getting type mismatch. And then it does some stuff, does a little bit of comparing, does a little bit of, FC error. FC error has something to do with negative numbers. So when you look a little deeper, you see that int convert is meant to be converting signed numbers, signed 16-bit numbers. That means anything in the range between negative, I think, 32767 and positive 32767. I'm probably off by one on one of the sides of that range. Anyway, anything in that range is cool. But if I were to give it a negative number that were too negative, or a positive number that were too positive, something that was outside of that range, even though it could fit unsigned into a 16-bit register, this routine would not like it. So what to do? How do I make this do a type conversion and just treat everything as unsigned? Well, I could just skip the check. Instead of calling int convert, I could just call B3FE. I mean, what could go wrong, right? So the only change is I'm going to add this symbol to start at B3FE. And then I use that symbol when I go to do my conversion. In fact, I don't even need this anymore, but I'm keeping it for old time's sake. So let's do a side-by-side comparison. On the left, we'll do the 8-bit version, and on the right, we'll do the 16-bit version. Which is faster? So in a surprising twist of fate, it seems like the code works, and it seems like it works double speed. But are we sure? Because I still have something kind of gnawing at me, this thing where I do this weird, did I get 65536, and if so, wrap it around to 0 by doing this kind of sleazy check. Am I really getting all the possible numbers? Is it really random? It looks random, but is it really random? The problem with testing it like I did before is it would take a lot of memory to keep track of every possible outcome and to count each possible outcome, because there are that many. And if I had a byte for each of those, I would be using up all 64K plus. If I used a bit for each of those, then it would be 64K divided by 8. I'd be using 8K just to keep track of stuff. So what I'd like to do is to kind of spot check. I'm going to pick a few values that I'm uncertain about and a couple values that I feel are kind of normal, and I'm going to just test those. I'm just going to count those. So I'm going to write some code that's going to test these values. So something very negative, a couple like around the borderline, this one that's as positive as it can get. Obviously I want to check my 0 wraparound, and then a couple other standard numbers. So imagine these are the outcomes I care about, and next to these I'm going to print the count, how many times each of those occur. So here's my test data. These are the test outcomes that I'm looking for. So you can see like right around this borderline of hex 8000, I'm going like one less and one more. Then this is my -1, and then, a couple other values. And this is coded as a struct, which this is the first time I've used structs with LWASM. So the way that works is you define your struct like this. So I'm going to call it test struct because this is the struct that comprises a single test case. And within a test case you have 3 fields. You have an outcome, which is 2 bytes, and that's these. So these are the ones, the bytes that translate into what you see in the comment on the right hand side. The next field is the count, so this will record how many times that outcome occurs, and we started off with just being 0, so 2 bytes of 0 each time around. And then finally, the line number that I want to print both the outcome and the count. So this is going to be like line 0, line 1, line 2. So this tells me where I'm going to print stuff. When you define a struct, what it does is it defines these symbols, outcome, count, and line, that are scoped to this and that result in the offset. So for example, when I initialize my screen like before, I clear it first, but then I go through a loop to print all of the outcomes. So here is the syntax you would see. You have the name of the struct, a dot, and then the name of the field. And then this is just a symbol that becomes the offset. So since outcome is the very first field, this is just a fancy symbol for the number 0. That's all this is. This just means 0. It's the offset. And so in this loop, I'm going to run through all the outcomes. I'm going to put them into the floating point accumulator so that I can then convert it to an ASCII string, and then I print it. And so you've seen stuff like this before. But what you haven't seen yet is this. This is how I'm going to advance X to the next entry. So I'm doing obviously an array of these structs. I probably should have mentioned that before. This is an array of them. So to advance X to the next element of the array, I have to go by the size. And this is a new symbol that I get defined for me when I make a struct. And this is simply, as you would guess, the number of bytes in that struct. So this just translates to that number. So this will increase X to the next one. I'd verify if I've hit the end, and if not, I loop back up. So this will print the outcomes. As the code is running, and it picks outcome after outcome, then I do my update stats section. So here's where I get to use some more of the structs. D represents the outcome from the random number generator, and so I ask in a loop, does it match the particular outcome of the struct that X is pointing to? And if not, I go to my continue, which advances to the next entry and loops back up. But if it does, then I get to go into the count. So I load D with what's sitting at the count field, add 1 to it, and I stick it back. I then convert that count into floating point accumulator, so I can convert that to a string, and then I get to print it. Printing requires that I know where in the screen I'm going to go. So this subroutine will ask, what screen address do I need to print the thing at? So assuming that X points at the beginning of the test struct entry that actually matters, I can go directly into the line field, and then I load up B with 32 so I can multiply them together, which is this. And then I just add in the very beginning of the screen buffer, which is this. I transfer that result to Y, and then Y is the register that my caller will use. And then after I return, I add this value so I get to the proper column. So the column that I'm using in each line is 15. So that covers this code, and this should test my code that generates random numbers. But how do we test the test?
What the hell Easy, miss. I've got you.
You've got me? Who's got you?
Normally I would just step through this in a debugger to make sure it's doing what it's supposed to do, but it could take a very long time before we come across one of the outcomes that's in our test case. So in order to force that to occur, we're going to use a feature of the debugger that lets us modify the state. So I'm going to set a breakpoint here, which I know happens every time an outcome occurs. And then at this point, I can change things to force this loop to actually believe that I've arrived at one of the outcomes. So to figure out where to set a breakpoint, I take a look at the output from LWASM, and that's this line here, which it tells me occurs at 3F80, so that will be my breakpoint. And here we are, stopped at 3F80. And I'm going to take a look at my registers. Now the D register is telling me the outcome from the random number. And I'm just going to change it. So I'm going to see, well, what happens if you think the outcome was 0? And you can do that with the do command. So do D equals 0. Now D is 0, and so it's just as if I naturally occurred at 0 as the outcome, even though I made it be rather artificial. So I will expect that I'm going to enter the loop, and that when I do this compare, it's going to be true. So rather than jumping forward to go to the next iteration, I should be incrementing the count and printing stuff. So here I am comparing D with what is at offset 0 in X, and X is pointing to the struct. And we're still here, we did not do the branch. So now we're going to load the current count into D. So D is still 0 because the current count is 0. I'm going to add 1 to D. D is 1. And I'm going to put that back into the struct. And then the next thing we're going to do is to convert the count into an ASCII string and print it. And then the next thing we're going to do is figure out where to put it and then to actually print it onto the screen. So here I'll be printing it onto the screen, and so I am going to show myself the screen. Now the width of this doesn't exactly match the width of the screen, but you get the idea. Here I'm printing out the different outcomes, 0, 16, 4096, and so on. So after this, we're going to expect to see a new 1 printed there for the count of 1. And sure enough, there it is, it shows up, so I printed my 1. I can't quite rely on this because the scan lines are not like doing a full wraparound every time I do a step. So as I'm stepping through, I'm going to have to rely on this. But I can repeat this process and try different outcomes and see what happens. But I'm just going to let it go. It's going to hit my breakpoint, which I'm just going to clear. And let it go for a bit. Oops. Breakpoint clear 1. I'll let it go for a bit, and then we should at least see the 1 show up, and sure enough. So I feel like my test is probably going to work. So maybe it's worth 30 minutes of my time to actually run this thing. So I let it go for about 30 minutes, and I'm going to do a time lapse for you so you can see the result. So as you see, things are updating pretty evenly. I seem to be getting all the outcomes at about the same rate, which makes me happy. I am now successfully generating random numbers twice as fast. So what will I do with all this garbage I can make? That will be in the next video.